Okay, time to get started. So, new topic today. We're going to talk about integrals and different coordinate systems. Now, this is actually an application of change of variables, and it's not always presented this way. I like to present this topic in this way because I think it's easier, really, ultimately, but it has different points of view. So, let me remind you, we have this existing idea of a polar coordinate system. And let's just look at this part of the picture right here. Polar coordinates says, I guess I'll zoom in here. Polar coordinates says that for a given point, I can describe its location in two different ways. I could talk about its x and y coordinates, horizontal, vertical axes and all that. Or, alternatively, I could think about this ray from the origin to that point and think about, on the one hand, the angle of that ray and the magnitude, the length of that ray. All right, so these are two different ways to describe the same point in the xy plane. So that's the old point of view on polar coordinates. Now I want to give you a different point of view. Note that we had these relationships between the rectangular coordinates and the polar coordinates. We thought of them at the time as just formulas, the way you convert from one to the other. Let's now reconceive of these as a function. Right? And so let me zoom back out now. So thought of as a function, these are a function from the r theta plane and into the xy plane. A perfectly reasonable way to think of these equations. X and y are the output coordinates. R and theta are the input coordinates. Now, why would I want to do that? What does that buy me? Well, interestingly, if you think of these old equations in this new way as a function, that function is a change of variables function. Right? And we just got through doing change of variables, and so this is a great opportunity to maybe apply the change of variables method to this particular function. So, again, here's that function. X and y are the good old existing formulas of r and theta. So here's an example of how some domains would be connected by way of this polar coordinates change of variables function. And I'm just going to look at this rectangle here and ask what's the image domain over there. And we're going to do this sort of one edge at a time. So what can I say about, well, let's do it like this. What can I say about that edge? Now, looking in the r theta plane, this edge is on the r-axis. So on this edge, theta equals 0, and r starts at 0 and goes to 1. What happens to x and y if theta is equal to 0 and r goes from 0 to 1? Well, it's this edge right there. Okay, right. Next, let's talk about that edge. That edge, theta is pi over 2, and r starts at 0 and ends at 1. So now let's do that in the xy plane. Theta is going to be pi over 2, so we're going to be on the y-axis, and r starts at 0, ends at 1. Right? And then you can sort of keep going. What can I say about this edge there? That's r equals 1, so we're going to be on the unit circle in the xy plane. We're going to start where theta equals 0 and end when theta equals pi over 2. So, that. And this last edge is kind of silly, really. But that edge, that's on r equals 0. R equals 0 is just this point. So in some sense, the way that this rectangle gets turned into this shape here involves taking this shape, and obviously it gets bent and kind of curved around. But among other things, this entire yellow line here gets smushed down to that single point. Okay. So, right, fine. So what we have then is that the image of this domain is that domain. This is perfectly set up for doing change of variables. And said differently, then, if I have an integral over this domain, did I give this a name? I guess I didn't give it a name. I'll call it D. I have a double integral, of course, over that domain, f dx dy. I could reasonably ask what is the corresponding integral over the unit square here. What's the integrand, etc. And of course, it'll be dr d theta. And we just want to know, well, what do I put in here? Everybody see the plan? Right. By the way, this is going to be a win. This is going to be good news. Right? Because look at this domain that we're starting with is a domain over, well, it's a curve. It's annoying. There's going to be square roots if we do this D domain in rectangular coordinate. The usual way, if we write this as a double integral, I'm going to have square roots in my bounds, and that's awkward. I'm going to be able to, doing a pullback with change of variables through this polar coordinates change of variables function, I'm going to be able to rewrite it as an integral over a rectangle. I called it a square. Shame on me. It's a rectangle. Okay. Right, so let's start the details. First thing I have to do is figure out what my stretching factor is. So I need to look at this function, which is here, and compute the Jacobian. Right? Take the determinant, take the absolute value. Usual formula from last time. And here's that calculation. Now, I'm going to leave some of this as algebra exercise for you guys, but these are the r partials of that function, and these are the theta partials of that function, and so therefore, assembling them as columns, that's your Jacobian matrix. And I'll let you guys check me on that. It's a couple of partial derivatives. Take the determinant. Don't forget to take absolute values. The determinant ends up being r, which is kind of nice. But don't forget the absolute values. Right? So absolute value of r is that determinant right off the bat. Now then I can come back up here and note that something nice about the picture. In this picture, r is always positive. Right? For every point in my new domain, there are no negative r's. So at this, given that r is in fact positive in this example, I can rewrite absolute value of r as just r. So there's my stretching factor. It worked out really conveniently, just r. Pretty happy? Okay. Right. So then the integral that I had over the original domain, this integral some function dx dy, I can rewrite the dx dy using the change of variables method. I just insert my Jacobian determinant. I just computed this Jacobian determinant, r. Right, the function itself is just a matter of plugging in what I already know about x and y. X is r cosine theta, y is r sine theta. And so altogether, that integral has turned into this integral. And it's a much easier integral to deal with than the original integral. Because again, this first integral is going to have square roots in the bounds. If you turn this, just slicing this up, it's got a circle, so you need square roots. No square roots. No circle. Right? This is an integral over a rectangle. Does everybody see how this works? This is a really nice application of change of variables. So it turns out that this change of variables function, or said differently, our polar coordinates conversion formulas, when thought of as a change of variables function, it's a surprisingly useful change of variables function. It's used surprisingly often. So often that I'm going to suggest that you, instead of reproducing instead of reproducing this calculation here every time, just memorize the result. And it's used often enough that you should have that memorized. So specifically, the stretching factor is r. Now, one little detail you have to be careful about. You only get r instead of absolute value of r because we took advantage of the fact that r was positive. So if you want to get rid of those absolute values, it is required that, in fact, that when you use polar coordinates to, as part of your change of variables to reproduce a domain in the xy plane, only use positive values of r. Don't do any negative r. But good news, that's convenient. We don't really like negative values of r anyway. So stick to the convenient choice of r being positive, and then your stretching factor really is just r. Said differently, you can just memorize this little equation that dx dy is r d theta. Does that make sense? In fact, why would you ever be doing an integral in the r theta plane? Why would you ever be doing this? Well, the only reason, as of now anyway, that we would have any reason to do an integral in this r theta plane is as part of a change of variables from the xy plane. So, in fact, I like to, this is just my point of view on this, I like to think of r d theta as kind of a single thing. That's what you might call dA. Right? That's what area looks like in polar coordinates. Say it differently. So I would encourage you, when you're writing down an integral, if you're planning to do it in polar coordinates, don't write down dr d theta by itself. Because it's never going to be alone. It's never going to be just dr d theta. It's always going to be r dr d theta. So if you decided you're going to do it in polar coordinates using this change of variables trick like we just saw, write down r dr d theta, and then you won't forget the r. I think that this is one of the most common mistakes that I see students make on exams when they're doing integrals with this, using the polar coordinates function as a change of variables. We're going to develop a different lingo for that very soon, by the way. But the most common mistake, one of the most common mistakes I see students make is they forget to include the stretching factor of r. And that's another motivation for don't ever write down dr d theta without the r in front of it. It'll help you not forget. So you can do something very similar with cylindrical coordinates. I'm going to be pretty quick with this because it's pretty much the same as polar coordinates, right? It's just there's an extra z coordinate, but that's kind of the same thing. So again, you can think of a point here. You can think of its cylindrical coordinates as these numbers that in the XYZ space describe the location of that point. Or you can think of those as separate axes, right? And you can think of the conversion formula between cylindrical and rectangular coordinates as being a function, which you could choose to view as a change of variables function, just like what we did in polar. So doing, here's your calculation for your Jacobian determinant. Interestingly, even though it's a different matrix because, well, it's a three-dimensional change of variables formula, it's a surprisingly similar result. It's still just r. Right, so when you're going to use cylindrical coordinates as a change of variables function, r is your stretching factor. Note that, again, that requires r to be positive in order to make that interpretation. So let's just always make those choices. Always choose r to be positive. And then you can convert integrals over awkwardly shaped regions in R3. You can convert them into integrals using cylindrical coordinates. And note, I've put the r in there. I've put at the same time r dr d theta dz, right? Because that r is always there. Okay. All right, so here's a specific example. Suppose that this is the domain that I'm interested in doing an integral over. Well, it's highly curved. No matter how you slice this up, if you do this in the usual triple integral method, you're going to have square roots somewhere. Highly undesirable. So how do we deal with this? Well, I'm going to deal with this by realizing that this shape is actually the image of a much more desirable shape in the r theta z space. And one at a time, you can just think about, well, what do these various faces look like? So, for example, let's look at this face. What is that? Well, that face is where theta equals 0, and r goes from 0 to 1, z goes from 0 to 3. So theta equals 0 is the xz plane here, and r goes from theta to 1, 0 to 1. Theta goes, z goes from 0 to 3. So that's the image of that. Similar argument. That theta equals pi, and r and z range in certain ways. So theta equals pi would mean that we're kind of over here now in the xyz space. That's where theta equals pi points. And so that describes actually that plane. So in some sense, what's happening here, this cylindrical coordinates change of variables function is taking this thing and it's kind of doing that, right? It's kind of stretching. I mean, this end here is being kind of worked, kind of wrapped around the z-axis in some sense. Just like with polar coordinates, there is something that's being squished. This entire face here, r equals 0. So that entire face is getting squished down to that little line segment on the z-axis. Nice. Kind of see what's going on here? Okay. So then what's happening to this face? Well, that face is where r equals 1. R equals 1 is a cylinder, thus the name cylindrical coordinates. Okay. So r equals 1, and sure, z goes from 0 to 3, but more interestingly, theta ranges from 0 to pi, all the while r equaling 1. And that turns that into that. Okay, everybody see what's going on here? See how this looks just like polar coordinates, just with an added third dimension here? Okay. So clearly this domain goes to that domain, and therefore an integral over this undesirable domain here. Instead, I could do the whole pullback thing. That's my new domain in r theta z coordinates. So z goes from 0 to 3. Theta goes from 0 to pi. And r goes from 0 to 1. Nice, easy bounds. Constants, right, much more desirable than the curved shape. Okay. Right. So let's talk about spherical coordinates. Now this really is going to be a little bit different. Spherical coordinates, you remember these equations. X, Y, and Z are these kind of annoying formulas involving sines and cosines and such. Rho, phi, and theta. Make sure that you're comfortable, by the way, with where these equations come from. Why is x equal to this? It's good to make sure that you can see that on the picture. Okay, so if I were to use this as a change of variables function, let's compute its stretching factor. And it's an imposing calculation. Here's what the Jacobian looks like. By the way, it'd be a good thing to check. And this is a good calculation. It's a good practice calculation to make sure that you're keeping up and that you have the necessary algebraic chops to be able to work through problems like this. So confirm me on that. So these are the rho partials and the phi partials and the theta partials. Take that determinant, and you'll notice I skipped all the algebra there. There's a significant amount of algebra that goes into that. But the Pythagorean identity kicks in multiple times, and it's really kind of beautiful how this all works out. That determinant ends up being absolute value of rho squared sine phi. It's not that bad. So I'm leaving this as I noted here as an exercise for the reader. That's you guys. So I encourage you to do that. It's not that bad, right? It'll take you a couple of minutes and maybe a half a page or a page of algebra. It's not that bad. Okay. So now there's that annoying absolute value. So how do we deal with the fact that there's that absolute value? Well, there's a very common misunderstanding. A lot of students think that, with polar coordinates, you just have to have R be positive, so with spherical coordinates, I guess you just need rho to be positive. And you see right here, that's not the problem, right? The thing that is going to make this expression possibly negative, it's got nothing to do with rho. Rho could be negative. Who cares? It's going to be squared. Rho squared is never negative. The problem is phi. Right? We need to make sure that sine phi is positive. That means that we need to make sure that phi, where did I write this down? There it is. We need to require phi to be between 0 and pi. Good news. That's what we wanted to do anyway, right? Phi, very naturally thought of as angle off of the z-axis. We'd like to think of it as being between 0 and pi, as I sort of go from the North Pole down to the South Pole. So again, good news. It's just that this is good news that we have to stick with, and it's kind of a requirement at this point. Okay. All right. Right. So integral might look like this. Here's an integral over some awkward domain, and if I do that integral using change of variables with this new spherical coordinates change of variables function, here's what dx, dy, dz turns into. Rho squared sine phi d rho d phi d theta. And again, I encourage you to think of that as a single thing. That's one object. In the same sense that we think of dx, dy, dz as, that's dv, right? This is a single object that's big. It represents the volume of a little box that we're multiplying by an integrand for whatever reason. Likewise, think of this as a single thing. Rho squared sine phi d rho d phi d theta, all in one. Okay, again, very, very common mistake is students will get the whole rest of the problem right and weirdly forget to put in rho squared sine phi. So this is a way to help protect yourself against that. Oops. Okay, so here is an example. Let's look at this dome. Now, y'all have written down some integrals, triple integrals over solids like this. Okay. Now let's try to talk about, what would this thing look like in spherical coordinates? If I were to try to find, said differently, a domain in rho phi theta space whose image is this half ball, this upper half ball, right? What would this other domain look like? Well, I claim it ends up being a rectangle, and let's again sort of think through the different faces of this rectangle. We'll start with this bottom face. What is that bottom face? Well, that bottom face is where theta equals 0. So that bottom face is going to be kind of in that plane. And specifically, it's the part of that where phi goes from 0 to pi over 2, and rho goes from 0 to 1. So it's that specifically. Oops, no, it's terrible. Let me try that again. It's that. Now, what about as I sort of move up a little higher? I don't know. What about this sort of slice in there? What does that look like? Well, it's the same range of rho, same range of phi. It's just that now theta is larger. So same basic picture, but just theta is larger, which in the XYZ space looks like this thing has been sort of rotated the way theta rotates around. And it goes all the way around, as it were, right? As theta increases, this goes all the way around until we get to where theta equals 2 pi, which of course is in the XYZ space the exact same thing here. That make sense? Okay, etc. for other planes if you'd like. Okay, so in some sense we're kind of done. I mean, this you really can do what I'd like to call integrals in these other coordinate systems in the way that we've described. Namely, you're going to view the conversion formulas, the various coordinate conversion formulas, as change of variables functions. We know what their stretching factors are. We've already computed them. Please memorize those formulas, the whole rho squared sine phi business, and the R. They're not that hard to memorize, so make sure to have those memorized. And then it's just a matter of plugging in and thinking through what the various domains look like. Right? The last thing I want to share with you is the way people actually think about these things. Most of the time, it's much more convenient than what I've been showing you. I just wanted to emphasize the change of variables point of view. But I'd like to point out that what we saw in this picture could more easily be viewed in a different way. In other words, as it turns out, I actually don't need to draw this picture at all. Said differently, everything that I need from this picture, I instead could just read straight off of this picture. And I'm going to start off with an example of this in polar coordinates, just a little bit easier to draw the picture. So we already saw how this domain is the image of that domain, and then we looked over here and asked, well, what's the range of values, on this domain here? Well, theta starts at 0, and then these are our theta slices, and theta ends at pi over 2. So it starts at 0, ends at pi over 2. And then we, on each one of those theta slices, talked about the range of values of R, and so R starts there and ends there, and that's fine. Let me just point out, though, that I can draw all these same conclusions while looking over here. And it's just a matter of interpreting correctly what do I mean by a theta slice. When I draw this theta slice here and say, well, that's what a slice looks like, when I set theta equal to, in this case, 0, and I'm taking a slice through that domain. Well, the equivalent thing in the XYZ space, theta equals 0, is just that. Increasing values of theta, if I look at other values of theta, other slices with different fixed values of theta, different theta slices, in other words. That's what those theta slices look like in the in the XY plane. Just different fixed values of theta. A fixed value of theta in the R theta plane is a horizontal cross-section, as it were. But a fixed value of theta over here is, it's kind of a pie slice, instead of a cake slice, I guess. I don't know. Does that make sense to everybody? Okay. All right. So you can, instead of saying theta starts at 0 and theta ends at pi over 2, you can draw the exact same conclusion over here. Theta starts at 0, theta ends at pi over 2. I don't need that. Right, same conclusion. This is a picture I already have. This is a picture I was given. Why don't we just infer straight from this picture? Right. Now, what about for the R coordinates? Do I have another picture down here? Yeah. For the R coordinates, so given that we've chosen now some value of theta between 0 and pi over 2, on the XY plane, here's a chosen value of theta somewhere between 0 and pi over 2. Okay. Yeah. So what's the range of values of R? Well, R starts at 0 and ends at 1. Somebody forget to roll up their windows? Yeah, it's coming. coming down pretty good. Same conclusion from this picture. R starts at 0. R ends at 1. It's just interpreting. Arguably, it's even easier to see in the xy plane because here we're interpreting R in the way that we are accustomed to interpreting R, namely as distance from the origin. It's a little bit weird. Think of this point over here in the r theta plane as where R equals 0 is. We're just kind of not accustomed to thinking of polar coordinates in that way. So again, this is really kind of an easier way to see it. So at this point, we don't need this picture at all. We've already memorized what the polar coordinate stretching factor is. The corresponding bounds that we need, we can see straight from the xy plane picture. We don't need this picture. All right. Okay, so let's look at this example here. So I'm going to do this integral, and I'm going to use this new point of view that we have. I'm going to think of everything in the xy plane. It's just that in the xy plane, I want to write down the integral where everything in the integral is done using a polar coordinates point of view on what we're looking at. So this is what we call doing the integral in polar coordinates. So our domain, top half of the unit disk here. And let's think about how I'd slice this up. How would I, what's the range of values of theta on this domain? Well, we start, our first theta slice is where theta is equal to 0. These are what theta slices continue to look like as theta increases, and it keeps going around until I get to my last theta slice where theta is pi. So theta goes from 0 to pi. And do I have that written down? Yeah, so theta goes from 0 to pi. And you can see here in the integral, we have theta going from 0 to pi. Okay. Here, let me do it like this. Theta, 0 to pi. Okay. Right. So now, what else do I need to know? Well, I need to know now the range of values of R, so I have to pick a theta slice, some arbitrary value of theta, somewhere between 0 and pi. And for that slice, I need to know, where does R start? Well, R clearly starts at 0, because that's the origin. That's R equals 0. And it ends when I get to that curve. Well, that curve is the unit circle where R equals 1. So R goes from 0 to 1. Okay. The integrand was given as x squared plus y squared. That's just rewriting. Again, there's nothing really happened there. X is r cosine theta, y is r sine theta. You plug in, fine, no big deal. Don't forget your stretching factor. Don't forget that dx dy is r d theta. Don't forget the r. It's really easy to forget the r. And then at this point, you notice that we get lucky, and not only did the bounds turn simpler, but the integrand simplifies very nicely. That's just r squared. That the r squared from the integrand combines with the r from the stretching factor and gives us r cubed as our new integrand. Everybody good? Okay, so we have now, without drawing anything, without drawing a change of variables function at all, we didn't re-envision a new r theta plane, right? Nevertheless, kind of under the surface, that's what we're kind of doing. It's just that everything that we need to see in doing that is on the picture we already have. Okay, so here's another one. So here we're doing an integral. And R is disk of radius A centered at A0. So this disk here. All right, so you want to think about what do these theta slices look like? Keep in mind, theta slices emanate from the origin. By the way, a common mistake is for students to sort of think of the theta slices as emanating from the center of the circle. They don't emanate, that's not how polar coordinates work, right? They emanate from the origin. If your circle is off center, well, so be it, but the theta slices emanate from the origin. Right. So, the first slice, negative pi over 2. Sequence of slices keeps going around. Last slice, positive pi over 2. So theta, negative pi over 2 to positive pi over 2. For a given value of theta, pick a theta, right? R starts at the origin, so R starts at 0, and then R ends at that point. What do we know about this point? Well, the point is on that circle. That circle has this equation. That equation you can convert into polar coordinates. And what it gives you is R equals 2a cosine theta. So this process here, again, that's an old chapter 1 thing. So we want to make sure that you still remember how to do that, how to convert an equation of a curve from rectangular coordinates to polar coordinates, and ditto for spherical, etc. And so that point, that point is on that blue curve with that equation, which is that equation. And so there's the ending value of R, 2a cosine theta. So we're going on, R goes from 0 to 2a cosine theta, like so. And again, you can combine the integrand, collect terms together. Don't forget your stretching factor. Again, world's easiest mistake to make. Forget your stretching factor. How we doing? Everybody happy? Okay, so roughly speaking, what I've been telling you is what coordinate slices look like in polar coordinates. So these are what theta coordinate slices look like. What I haven't mentioned is what R coordinate slices look like. We kind of haven't needed to know what the R coordinate slices look like, but if you think about it, a coordinate slice just says what happens when you set that variable equal to a constant. This is what it looks like when theta equals a constant. So what does it look like when R is equal to a constant? Well, these are what you might call R slices. And they're just concentric circles centered at the origin. Once you've done theta slices, of course, those are just values of R as you move along a theta slice. So that's why we haven't needed to make such drawings yet. But you might, conceivably, at some point, want to do your slicing in a different order. Now, this is a rare choice. I just kind of want to show you just to be thorough, so you can kind of see for yourself why you, in fact, most of the time are not going to make this choice. But let's suppose instead of doing the theta slicing first and then the R slicing after that, let's do our R slicing first and then our theta slicing after that. So that being said, what's the range of values of R here? Well, your first R slice is 0. And this is what R slices look like. Bad drawing, but this is what R slices look like as you keep going. And the last one is where R equals 1. So you could start with R going from 0 to 1. Here we go. R goes from 0 to 1. And then, for a given R slice, on that R slice, what's the range of values of theta? Well, theta starts there at 0, and then theta moves along until you get to that point where theta is pi. So theta goes from 0 to pi. And it's still the same stretching factor, so it's still r that goes there. So dx dy is still r dr d theta. It's just that here I've decided to put the d theta before the dr. And fine, it's an alternative way to sort of break down that problem. Suit yourself, do it whichever way you like. I find this to be a much more awkward picture because the slices aren't even straight. What kind of a knife do you use to make a cut like that? You know, it's harder to draw the picture. It's harder to visualize. In this case, we end up with algebra that's sort of comparably convenient, sure. But did this buy us anything? Not really. This is not a win. This is a draw. Right? Now let me show you how it can be a loss if you try to do that same sort of thing in a situation like this. Right? We looked at this problem previously, and if I started doing r slices here, you can see my pictures are pretty weird. Right? That's drawable. It's fine. I suppose you can do that. But then next question, what's the range of values of theta? So if I ask, well, what's theta there and what's theta there? Oh, okay, well, that is pretty weird. We need to solve for theta then as a function of r. And you end up with a pretty undesirable result. You've got arc cosines in your bounds. I'm going to let you guys read the details on that if you're interested. Alternatively, feel free to just be sold that you shouldn't do it this way. Right? So, in other words, putting your differential in this order, doing r d theta dr, could make it much worse. Best case scenario, it makes it no better than what we had before. It's a loser. So, side note, there are some rare circumstances, unusual rare circumstances, where it is actually more convenient to do the slicing in that order. They're extremely rare. They're so rare that I think it's a reasonably good instinct to simply just always do it r d theta, and just don't ever do this. Is that cool? Right. Okay. So, yeah. So what about in other coordinate systems? This is what coordinate slices look like in cylindrical coordinates. So when you set r equal to a constant, you get a cylinder, again, thus the name cylindrical coordinates. If you set theta equal to a constant, you get these planes. If you set z equal to a constant, you get those planes. So when you're deciding which order you want to do your slicing in cylindrical coordinates, if you're going to do an integral in cylindrical coordinates, I encourage you not to do your r slicing first, because now you're drawing weird pictures, right? It's a tough draw. It also is going to create algebraic awkwardness often, so it's a bad idea. I would encourage you to always do your theta slicing before your r slicing. The reason for that is that once you've done theta slicing like that, what is now an r slice? What does that r slice look like on a theta slice? Well, it's a straight line. Right, so if you do your theta slicing first, you're not going to really be drawing these cylinders. You just need to know what do these cylinders look like as they intersect one of these planes, and it's a straight line, and that's not bad. Right? So as long as you, in some sense, have your dr further inside than your d theta, no problem. Now you could do your dz slicing before all of this, right? In which case, in that plane, your theta slices would look like that, and then your r slices are just, what's the range of values of r on there? And that's perfectly fine, right? So doing this z slicing first, perfectly fine. As long as you do your r slices further to the inside than your z slices. So these are basically, not exactly, but roughly the only choices certainly the only choices you have any reasonable need to consider are r dr d theta dz and r dz dr d theta. Pretty much those are the only two you're ever going to need. So in particular, dr and d theta are always together as a group with r further inside than theta, and then the dz either before or after that pair. So stick with these, you'll be fine. How are we doing? Okay. All right. I'm going to let you guys read this example. I'll go ahead and do this example. It's a quick example. So here we want to talk about this cone. And what if this was my domain for a triple integral? How would I slice this up? Well, I'm going to do this with cylindrical coordinates. I'm going to do my dz slicing on the outside. You'll notice, so z slicing on the outside, and I have z going from 0 to 1 because, well, z starts at 0 and z ends at 1. Then range of values of theta. Well, on any z slice, on any z slice, theta, color am I doing? Green. Theta starts at 0. It goes all the way around and ends at 2 pi. So theta, 0 to 2 pi. And then you just need to know, okay, so then for a particular z and for a particular theta, you know, what can I say about that point? What can I say about, what's the equation of that line, as it were, that goes from where, let me write this down, r equals 0 and z equals 1, and it goes all the way down to where r equals 1, z equals 0. That's not hard to persuade yourself that the equation is r equals 1 minus z. So r goes from 0 to 1 minus z. That makes sense? Okay. Right. So let's see how this looks in spherical coordinates. This is a tougher collection of pictures to deal with. This is what your spherical coordinate slices look like. So this is what happens when you set rho equal to a constant. You get a sphere. Again, thus the name, spherical coordinates. If you set phi equal to a constant, well, you get a cone. That's a pretty tough draw as well, especially if you're thinking about how this phi slice intersects some other solid that you were given. It's very artistically challenging, not to mention visualization challenging. And here's your theta slices. Again, conveniently, theta slices look kind of nice. So this is a bad news, good news deal. The bad news is that these pictures here are hard and undesirable. The good news is it makes for an obvious first choice. For slicing, always do your theta slicing first. All right. Now, next, what should I do, phi or rho next? Well, if I do my rho slicing next, a rho slice, as it would appear on one of these theta slices, would be a half circle. I don't like that so much. Whereas one of these phi slices on this theta slice, straight line. So let's not do that, and let's instead do phi as my second choice. And then theta, a rho, can kind of do whatever it wants. Okay. So bad news, good news. The bad news is that some of these slices are awkward. The good news is that narrows down your choices. You really should only do your spherical coordinate slicing and really in one order, and that is to do theta slicing first, phi slicing second, and row slicing third. In other words, always do it in this order here. D rho d phi d theta. And again, you're not going to write down d rho d phi d theta without first writing down the stretching factor as part of it. You think of this as a single unit, so rho squared sine phi d rho d phi d theta. Not only is this always what your spherical coordinates dv looks like, it's always going to be in this order. Very rare and weird counterexamples that are effectively not worth worrying about. Okay, so that's the good news. So let's take an example. How do we draw these cross sections, keeping in mind that we're going to be going in this order, theta first. So let's look at this domain. So this is a sphere, offset, centered at A on the z-axis. This is a sphere of radius A, so it sort of sideswipes the xy plane at the origin. Right? And we know we're doing theta slicing first, so we want to ask on this solid here, what's the range of values of theta? And well, theta is going to start at 0, and then it goes all the way around and ends at 2 pi. Everybody see that? Any questions about that? So theta, 0 to 2 pi. Now, next we're going to look at a particular theta slice, and we want to ask next, what is the range of values of phi on that theta slice? So going back to here, we're going to look at some arbitrary fixed theta slice. Here it is. There's a theta slice, so that again is we're choosing and fixing a particular value of theta. And on that theta slice, I want to know the range of values of my next variable phi. Again, because I don't want to draw awkward and difficult pictures. So on this, what's the range of values of phi? Now it's a hard thing to visualize, right? This plane cross-section of this sphere we're looking at it from a weird angle, and you can probably kind of think it through. But let me just point out there is an easier way to think about this, and that is to go ahead and take the moment to draw what that theta slice looks like, sort of looking at it straight, as it were, right? In other words, here's that slice. There's this theta plane. It's the exact same thing that I have drawn here. I'm just redrawing it, looking at it straight on. I don't really need the rest of the solid anymore. Everything else I'm going to be doing is going to be looking only on this theta slice, so let's make it easy to look at. Everybody on board? Okay. So on this picture, phi slices look like that. Okay. So here's where we start. We start with phi equals 0. These are what these phi slices look like. They get shorter and shorter and end at pi over 2. Again, keep in mind, critical point, they emanate from the origin. They don't emanate from the center of what you might happen to be looking at. Right? Very common mistake. So they emanate, because they're emanating from the origin, that's why it sort of stops at pi over 2. There's just there's nothing down there. Right, let me do this in red. There's nothing down there. So yeah, so phi goes from 0 to pi over 2. Oh, I did that in the wrong color. Well, phi 0 to pi over 2. Now, I want to focus my attention. Keep in mind, we had theta chosen. Now we have phi. We have a range of values of phi, so we're going to choose a value of phi. So on this theta slice, I'm going to choose an arbitrary phi slice of that theta slice. And now it's on that phi slice of that theta slice that I want to know what's the range of values of rho. So on this picture, well, rho starts there. Rho ends at that point. So what can I say about rho at these 2 points? Well, let's remind ourselves where this picture came from. What is that point? Well, that point came from there. That's the origin. Rho equals 0. What about this point? Well, that point's on. It's on this circle cross section. That circle cross section came from this circle. It's on, which is a cross section of this sphere. So the point there in question is a point on the sphere. So what I really need to know then is on the sphere, what is rho as a function of phi and theta. And I need to know it as a function of phi and theta because phi and theta have been chosen. All right, so I get to use those. So said differently, I need to know the spherical coordinates equation of the sphere. And that, again, is a Chapter 1 problem. Right? So you just have to write down the rectangular equation of the sphere, plug in the conversion formulas, and find the spherical equation then of that sphere. And what it turns out to be, conveniently, it comes in the form where rho is solved for, and rho we know starts at 0, but it ends at 2a cosine phi. So I'm going to let you guys again work out the details of that. Make sure that you remember how to do that. Find that upper bound. Everybody good? Okay. So in this case, notice that your integral, we have a new integral to look at here. It's a little undesirable. You notice that in the inside-most integral, if you were to imagine the process of cranking this out, right? So you're going to do a d-rho integral first. So you're going to have rho to the fifth is going to show up. You're going to plug in these bounds. And so pretty quickly you're going to find yourself dealing with cosine phi to the fifth. And that's a little annoying, but it's perfectly doable, right? So there are single variable calculus techniques that allow you to make clever Pythagorean substitutions and work out an integral like that. It's not that bad. If you're a little rusty on it, again, now might be a good time to remind yourself how those various trig integrals that you studied back in Math 122L, how those go. Okay. So doable, by the way. Now let me just remind you, what was the alternative? The alternative was to do the integral in rectangular coordinates, in which case I would have square roots everywhere, and those are much more annoying, much less convenient, and sometimes intractable. Okay, well, that's it for integrals and coordinate systems. A bunch of exercises for you. We're going to move on to the next section now, scalar line integrals, and this is just another kind of an integral. Let's count integrals. How many kinds of integrals have we talked about so far? We've talked about single variable integrals, as a review, and then double integrals and triple integrals. So now this is going to be our fourth kind of integral. It's going to be a different sort of a Riemann sum, but ultimately it is going to be a Riemann sum. It's going to follow all those four integral conditions that we talked about way back when, right? When we were first doing integrals. So, said differently, it's a different kind of a domain, but for whatever reason, why I'd want to do this, talk about in a moment. But I'm going to take this domain, this is a curve in space, and I'm going to find reasons why I might want to take this domain, chop it up into little pieces, and on each little piece, for some reason appropriate to the application, multiply the size of the piece, size in this case being length, times the value of the integrand, again, appropriate to the application, whatever that happens to be. So I just want to point out before we get started that this is a new kind of a question. We've talked about single variable integrals, sure. But the domain, when you're doing single variable integrals, is an interval on an axis, right? It's an interval on the, let's say, the x-axis or the t-axis or something. This is kind of like that in that we're breaking this up into little pieces that have length, and you could say this is a one-dimensional domain, but it's not on an axis. It's floating up in space somewhere. So it's not a single variable integral as we've written it here. It's not a single variable integral because it's taking place in three-dimensional space. So the next question is, well, why don't we view this as a triple integral? Well, triple integrals, when we talk about the volume of the pieces that we break things up into, these pieces are little pieces of curve. They don't have volume. And so that doesn't really make sense either. So it's this dimensionally awkward thing where we have a one-dimensional domain that lives in a three-dimensional world. So we're good already with one-dimensional domains in a one-dimensional world, two-dimensional domains in a two-dimensional world. That's double integrals. Three-dimensional domain, three-dimensional world. Triple integrals. Now we've got this problem. We've got a mismatch. So we have to come up with a new kind of a Riemann sum. Now let me say a few words about why we'd be interested in such a thing. Here's a physically plausible question. Here is a metal rod that's been bent around and twisted around in some way, and it's sitting in space here. And maybe this metal rod, like metal rods that we considered in the past, has a non-constant density. And I want to compute the mass of this thing. Well, I need an integral. I need to chop this up into little pieces. On each little piece, multiply the length times the mass per unit length of that location. That's an integral. It's an integral on a domain that we're not armed to deal with at this point. Does that make sense? Okay. Right. So here's the idea. I'm going to take this curve, chop it up into little pieces. One of the little pieces, for example, might look like that. Now here's an exploded view of that piece. I'm just kind of zooming in. That piece, I'm going to be interested in the size of the piece. That's the length. That's what I'm going to call delta S. Right, that's the length of that little piece of curve. And then I'm going to need to multiply by the value of some integrand function. That integrand function, though, is going to have to be evaluated at a point on the curve. So I need to pick some point I'm going to call xi that's on the curve. Okay. And so here we go. The size of the piece times the value of your integrand at a point on the curve. Motivated by this picture. Is everybody happy? Any questions? Now again, keep in mind, let's not worry about how we're going to calculate these things just at this particular moment. So the point here is simply to create an algebraic construction that allows me to get a foot in the door, kind of get my hands on the problem of how do I deal with computing the mass of a thing like this, and to write that down algebraically. And this is how we write that down algebraically. We'll talk later about how to actually compute such a thing. Right, okay, fine. So let's see some examples where this applies. Here's the one we've already kind of talked about. If I have a bent rod following a curved path with a non-constant density, note density here depends on location. Okay. How would I compute the mass? Well, mass accumulates. Total mass is the sum of the little pieces of mass once I chop it up. And furthermore, on each little piece, mass is density times length. Right? Everybody good? Okay. Here's a different example. And again, I just want to show you another example that, sometimes these things come up semi-unexpectedly. But suppose we have a snow problem. Suppose this is our driveway. And used to live in a house that had a long driveway like that. And suppose it's snowing, and there's an accumulation of snow, and let's suppose we know what the function is that tells us height, depth of snow accumulation at any random point on our property there. Okay, so how would I compute the total mass of snow? For example, if you're entertaining the question of how much snow am I going to have to shovel, right? That's a pretty interesting question if you're the one doing the shoveling. So this is a pretty relevant integral to want to compute. Okay. So how would you do that? Well, a reasonable choice is to take this driveway and chop it up into little pieces. Again, here's an exploded view of that little piece. And on some little piece of driveway, road, driveway, whatever, some little piece of length ds, well, that little piece of driveway has a width, so there's a corresponding area of that piece of driveway, and if you multiply that times the height of the snow, I'm probably exaggerating here a little bit, but seems like it was that high. If you multiply by the height there, h, then the amount of volume of snow on that short little piece of the driveway is, well, it's going to be h times w times ds. There you go. Right, and that's what's going to add up. I mean, snow accumulates. That was kind of an awkward pun. Snow, the volume of snow on your entire driveway is an accumulation in the sense that the total volume of snow is the sum of the volumes on these little slices you might chop it up into. And on each little piece, the volume is width times height times ds. So in this case, again, I claim this naturally fits as an integral in the sense that there is a function which, appropriate to this particular application, there's a function there that you multiply by length of that piece of curve to get the quantity that you're adding up over the curve. All right, so again, just kind of like with flow rates. You remember when we did that flow rate problem, there was an application of double integrals that it didn't at first seem like there'd be something you just multiply by area. Likewise here, it doesn't seem necessarily like something that you would just multiply by ds, and that you could therefore view this as an integral. But that's how it turned out. It ended up being that the thing that we're adding up is, in fact, something times ds. So sort of an unexpected integral. Okay. All right, so now let's talk about how to compute these things. Here's the basic idea. We have curves. Here's a parametric curve. Here's a curve. And let's imagine that we were to parameterize the curve. So I want to view that curve as then the image of a piece of the t-axis. Now, this is an old picture, right? Parametric curve, where we view the curve as the image of an interval on the t-axis. How does this help us in this case? Well, this helps us because this should be vaguely suggestive of an idea that we've talked about in the last couple of days. Namely, I have a domain over which I'm interested in doing an integral. That being the image of a different domain that I find more desirable. Previously, this is some bumpy, wiggly shape, and this was, let's say, a rectangle or a rectangular box or something like that. And in this case, it's just that now, instead of having a shape awkwardness, now we have a dimensional awkwardness. This is, it's a one-dimensional thing in a three-dimensional world, but it's the image of something that's dimensionally natural. One-dimensional interval on a one-dimensional t-axis, and that's, again, something we know how to deal with this. So we're going to use the same basic idea that we did with change of variables. Namely, I've got an integral here, and I'm going to use this function to simply rewrite all the stuff in XYZ space. Just going to rewrite it over here. So we'll turn an integral, this awkward integral, into a familiar integral. So it's a pullback, just like we did with change of variables. Okay. Right, so most of the work is in figuring out the stretching factor. So specifically, now this is a lot like what I did with change of variables. We're going to chop this up into little pieces. Correspondingly, that's effectively going to chop up the curve into little pieces. Like that, right? And what I'd like to know is, if I look at a particular little piece on the t-axis of size dt, let me circle that better. If I want to talk about its image piece of curve there, that's going to have length ds. I want to know, what does this x function do? How much does this dt get sort of stretched out to become this ds? So it's stretching factor, right? Again, I want to know what's the proportion that this ds is what sort of a factor times dt. So the way we're going to get our hands on that is I'm just going to compute ds here. I'm going to try to write down what I know about ds, and it's going to end up being, the result we're going to get for ds is that it's a certain factor times dt. It's just kind of nice how this works out. Okay. Here's the picture we're going to be looking at. Again, I'm going to think about these pieces of these various domains as relating to vectors. I'm going to think of this subinterval on the t-axis as relating to this little vector e1 dt. Then it's already drawn on there, but it's so small I'm not going to try to draw it again. So that little vector e1 dt is a vector that points exactly along that little subinterval, and having multiplied e1 times dt, the length of that vector is exactly the length of the subinterval dt. So e1 dt is a vector representing that little subinterval. What I want to know is this vector. Namely, when I plug this into the so given this change, this e1 dt change in the input, I want to know what is the corresponding vector, this dx vector change in the output. And then the thing I'm interested in, what I'm really interested in, of course, is ds, and the idea is that ds is the length of that vector. Okay, but let's start with just finding the dx vector first. Again, this is a perfect Chapter 4 question. I have an input change. I'm interested in the corresponding output change. We have exactly the tool that does this. It's the derivative transformation. Right, so I just want to apply the derivative transformation to this input vector, and that'll give me this corresponding dx output vector. And here it is. The dx, whoops, oh, it's not letting me, hang on. The dx output vector that I want is what I get when I apply the derivative transformation to this e1 dt input vector. So, chapter 4, right? Derivative transformation turns input vector into output vector. Now let's simplify this a little bit. The dt, being a scalar, factors out. What is left over is not only a unit directional derivative, but it's a unit directional derivative in the direction of a standard basis vector. It's partial derivative. But there's only one variable, so in fact it's just a straight up derivative And we know what derivatives are. A derivative of a parametric curve is the velocity vector. So dx is just velocity times dt. Now, that's actually a fairly natural conclusion to come to, right? I mean, if you want to know how much have you moved, well, velocity times time. Displacement, velocity times time. That's an old sort of result. I wanted to show you this point of view on it because there's future situations that are going to be coming up very soon where we will need this derivative transformation point of view, and this sort of lays a good sort of groundwork, a sort of first example. The punchline then is that again, the length we're interested in is the magnitude of that vector, and so it's just magnitude of the velocity times dt. So speed times time. Distance equals speed times time. Okay. And all of that fits together to give us this theorem. That is, if you want to compute one of these, what we call scalar line integrals, you do it with a pullback. You parameterize the curve, so x is just x of t. You plug in, and you compute ds with that stretching factor that we just computed, which is the magnitude of the velocity vector. So, punchline, these brand new kind of integrals that we wanted to compute, I can compute with a single variable integral. And I'm out of time now, so we'll quit here for today and pick up here on Monday.